Salut tout le monde. Welcome back to my channel, Anthony Makes Videos. I'm Anthony, obviously. And if you're new, you are watching the 24th episode of my differential geometry reading stream series, where I've been reading the entire book, Differential Geometry by Erwin Kreisig, out loud, that is. So this is not a podcast, this is not a course, this is not a class, this is not an audiobook. I intend that soon these will be live more often and actually streamed, but for now they're better in this edited kind of artificial stream format, sort of. But in the meantime, these also have a sort of like stream of consciousness quality to them, sort of like how Timaeus just was ranting for 50 uninterrupted pages at the end of the so-called Platonic dialogue. But anyways, we're currently in chapter 6 on mappings, in section 61 on conformal mappings, which starts on page 193. But first, I'd like to respond to this week's viewer comment of the week. And before I do so, as a reminder, I encourage you to comment below, and your comment could be featured as a comment of the week in a future episode. So without any further ado, this week's viewer comment is from Ambrosia with 3 A's on the end. I have never seen a concept like this on educational YouTube. I look forward to seeing more videos like these. Subscribed. Thank you. Edit. Are you looking forward to doing this idea but with calculus? Okay, great question. And this is sort of like thinking about the relationship between differential geometry and calculus, let's say. And I think this is a good entryway to sort of get into today's topic. And it seems like kind of a simple question, but I think it's important to sort of contextualize differential geometry in the overall mathematical landscape for a little bit. So I like to think that in a way these videos are already about calculus, if you really think about it. And I'm going to explain what I mean by that. So for argument's sake, we could just reduce, let's say, just calculus into any material that could be traditionally broadly taught in Calc 1, let's say, on limits and derivatives, and you have Calc 2 on integration and infinite series, and you have Calc 3 doing basically everything in Calc 1 and 2 but in higher dimensions. And you call that vector calculus, right? So let's just bundle up those things together and just call that calculus for now. And so when you're learning about calculus, the story is something like, once upon a time there was a man named Isaac Newton, and in physics, this guy Newton came up with these 3 laws of motion, and the second law is F equals ma, and this A stands for acceleration, which is a second derivative. And so you might say, well, what's a second derivative, you might ask? What's a derivative at all? And so we go from physics back to math, and by the time that we're done answering that question, Calc 1 is basically over and we live in a billiard ball universe. So then at that point, you take the reverse of a derivative, you call them integrals, and then since the first time around you basically just did everything in 2D, you start over and you do everything again in 3D. And so at this point, Calc 1, Calc 2, and Calc 3 are over. So then we can play a game where we start with the derivatives with some conditions, and we want the functions that when differentiated result in these derivatives that we started with. And so long as we only take derivatives with respect to one variable, then they're ordinary differential equations. And if we allow derivatives of more than one variable, then they're partial differential equations. So All of this material could be presented to someone who could then become adept at performing some sort of like computations along these ideas, and they could have a working conceptual vocabulary to that end. But some would say that that person still doesn't have the full picture of calculus. So you get the complete picture, or close to a complete picture, you could say, when you start to build up step by step with formal logical proofs what seems in retrospect so obvious, all of those layers of abstraction that you built up starting from derivatives going all the way to partial differential equations. So once you have the notion of taking a derivative of a function in one variable, it kind of seems obvious then that the furthest extent of generalization is finding a solution to a system of partial differential equations, right? So this entire development of calculus is now generally called analysis in math. So all else being said, the climb of pure abstraction also seems like a trivial afterthought in light of the path of the historical development of this subject area, you know. So from Newton ripping off Fermat, who was arguing with Descartes about the method for finding a tangent, all the way to Papa Rudin, there's been a lot of work on the rigorous proof side of things, and there's been a lot of motivation from problems in physics along the way. So in earlier differential geometry streams, I brought up this feud between Fermat and Descartes and how Newton just basically slapped a limit on top of what Fermat had done as an aside from discussing the overall choice of representing curves in the theory of curves chapter in this book. Also, this book interestingly uses a mix of Newton's fly dot derivative notation and Leibniz's infinitesimal d notation. Of course, if you've been watching these so far, Newton's fly dot notation is for derivatives with respect to arc length, or as we often refer to, lowercase s in this. Leibniz's usage of infinitesimals was controversially imprecise, but arguments surrounding this led to the ideas of Weierstrass and others in the 19th century, which today are the rigorous concepts which are introduced in, say, an undergraduate real analysis course. So, being that differential geometry is admittedly involved in understanding general relativity, gravity, in an earlier differential geometry reading stream, we looked at the philosophical turns from Ptolemy to Einstein. And along the way, we remembered how part of the debate between Newton and Leibniz wasn't just notation or who's the true inventor of calculus, but it was also a philosophical debate about notions of absolute space, which attracted none other than Immanuel Kant, whose progress on the topic partly constitutes his overall philosophy of transcendental idealism. We also envisioned, on our tour of one of the halls of the great mathematical wonders of the world, going in and seeing Scipione del Ferro and Antonio Fior, Niccolo Tartaglia, Ludovico Ferrari, and Girolamo Cardano discovering or inventing imaginary numbers, working on the solutions of cubic equations. And in that hall, we come upon then Augustin Louis Cauchy, who did a lot of heavy lifting to develop calculus with these imaginary numbers, complex numbers, if you will. And so now we have what we now call complex analysis. And so, of course, Euler and Gauss made big, major contributions to this field. But I talked about how one of the crown jewels of mathematics, in my opinion, is Cauchy's residue theorem. Now, some would say that a more important result from complex analysis is something that comes up in complex analysis maybe just before or right as you get to Cauchy's residue theorem in a complex variables course. And that result is the analyticity of holomorphic functions, which I'll explain what that means here right now. In short, a complex valued function f of a complex variable z that is analytic implies that it is holomorphic. And conversely, if that function were holomorphic, that would likewise imply that that function is analytic. So to quickly define these two terms, analytic and holomorphic, a complex valued function of a complex variable is analytic at some point A if in some disk centered at A, it can be expanded as a convergent power series. Namely, we have the function f of z equals the sum from n equals 0 to infinity of c sub n times the quantity z minus a, closed quantity to the power of n. On the other hand, a complex valued function of a complex variable is holomorphic at a point A if it is differentiable at every point within some disk or neighborhood centered at that point A, which then brings us to what today's differential geometry reading stream is about, conformal mappings. All right, so now we're going to read from Wikipedia, as I love to do in these, of course. So a conformal map is a function that locally preserves angles, but not necessarily lengths in general terms. So more formally, let U and V be open subsets of a space like, say, n-dimensional real numbers. A function f from the open subset capital U to the open subset capital V is called conformal or angle preserving at a point lowercase u naught in the open subset capital U if it preserves angles between directed curves through that point lowercase u naught, as well as preserving orientation at the associated f of lowercase u naught in the open subset capital V. And I haven't forgotten that this is all ultimately a response to the viewer comment of the week from Ambrosia with 3 A's on the end. And it'll all make sense momentarily. Just bear with me for a little bit longer. So now let capital U be an open subset of, say, the complex plane C, and let lowercase f be a function from capital U, this open subset of the complex plane, to then the complex plane itself, C. So this function f is conformal at a point lowercase u naught in capital U, the open subset of the complex plane C, in the same angle preserving sense that I just mentioned if f is holomorphic and its derivative is non-zero everywhere on capital U, the open subset. Furthermore, if f is anti-holomorphic, that is to say f is conjugate to a holomorphic function, it preserves angles but reverses their orientation. Now, before I keep going, I just want to pause so we can now reflect on the original viewer comment of the week. Are you looking forward to doing this idea but with calculus? Now, the obvious answer, which I'm not going to give, is that the offshoot of Newton's calculus from the geometrical interpretation of the derivative as the tangent line is in some ways the start of pre-modern differential geometry, when the introduction of differentials and infinitesimals led to a field of results distinct from the prior Cartesian analytical geometry. So I'm not going to give that answer. Another obvious answer that I'm not going to give, but I'm going to mention anyways, is that topics like derivatives of parametric representations of plane curves, the integral of arc length, and volumes of revolution are Calc 2 topics which are touched on in relation to previous sections within this book, that is. Also, the topics of Frenet frames and the classification of points on surfaces such as saddle points, parabolic and ellipse points come up in Calc 3 in vector calculus. Also, if you go to the Wikipedia page for directional derivative, which directional derivatives, I would argue, some would say is admittedly a Calc 3 topic, you can scroll down on that Wikipedia page article and there's an in differential geometry section. So looking at directional derivatives, but then within differential geometry, which you won't see that within a Calc 3 course, but, you know, shows the overlap there. And while there has been an odd Jacobian here and there thus far, the next chapter after mapping, so chapter 7 coming up, is on absolute differentiation, which I haven't read yet, but by the title at a glance, that seems to exude the calculus indeed. So giving me ideas about from Calc 3, when you take a directional derivative on a surface, there isn't the unambiguous direction that that derivative could be in. Anyways, the answer I'm going to give instead is that now, here in section 61 on conformal mappings in the differential geometry book, we're seeing a concept that might at first glance be categorized under complex analysis, which of course, as we all appreciate, is calculus with complex numbers, but we're about to appreciate conformal mappings now in a differential geometry context. So of course, like I just mentioned, Jacobians, the conformal property may be described in terms of the Jacobian derivative matrix of a coordinate transformation. The transformation is conformal whenever the Jacobian at each point is a positive scalar times a rotation matrix that is orthogonal with determinant 1. And going on a little further here, we have for mappings in 2 dimensions, the orientation preserving conformal mappings are precisely the locally invertible complex analytic functions. In 3 and higher dimensions, Louisville's theorem sharply limits the conformal mappings to a few types. And you may be saying, Anthony, why are you just straight up reading Wikipedia? Well, like I said, this will all converge upon something in a little bit here. So I'm just reading this off so that we don't have to jump through a rabbit hole dive of Wikipedia page reading. I've already done that for you. This is what I found. Joseph Louisville's theorem on conformal mappings states that every smooth conformal mapping on a domain of n-dimensional real numbers where n is at least greater than 2, these can be expressed as a composition of translations, similarities, orthogonal transformations, and inversions. Namely, they are what's called Mobius transformations, in this case in n dimensions. We are going to have a little bit of a rant about Mobius transformations coming up, so get prepared for that. So Louisville's theorem severely limits the variety of possible conforming mappings in 3-dimensional real numbers and higher dimensional spaces. By contrast, conformal mappings in 2-dimensional real space can be much more complicated. For example, all simply connected planar domains are conformally equivalent by the Riemann mapping theorem. Continuing on, that's bringing up more stuff where we're curious, we want to dive down this rabbit hole, search through Wikipedia. Okay, we're reading on. The Riemann mapping theorem, one of the profound results of complex analysis, some would say next to the analytic holomorphic theorem and Cauchy's residue theorem, of course, as we all know, states that any non-empty open simply connected proper subset of the complex numbers admits a bijective conformal map to the open unit disk in the complex plane. Informally, this means that any blob can be transformed into a perfect circle by some conformal map. Don't you just love that in math when you have all of this very technical, verbose jargon, and then you just have something that says, this means that any blob can be transformed into a perfect circle by some conformal map. We love it because we scroll down here through applications, and we have cartography, which we're going to actually come to in some sections right after this one, namely about stereographic projection and things like Mercator map projection. And funny enough, those map projection sections from this book, Differential Geometry, are like the only thing that gets cited in the other like differential geometry book that's like kind of like on this same level, which is the Kuhnel differential geometry book. So this Kreisig differential geometry book is cited in the Kuhnel book for the Mercator mapping stuff, which is coming up after this. Anyways, continuing to get sidetracked, we're in the applications, Maxwell's equations we're going to skip over, and oh, what do we have here? Surprise, surprise, we're in differential geometry, we have a reference to general relativity, and it says here, on the conformal map Wikipedia page, applications, general relativity. In general relativity, conformal maps are the simplest and thus most common type of causal transformations. Physically, these describe different universes in which all the same events and interactions are still causally possible, but a new additional force is necessary to effect this. That is, replication of all the same trajectories would necessitate departures from geodesic motion because the metric tensor is different. Makes sense. It is often used to try to make models amenable to extension beyond curvature singularities. For example, to permit description of the universe even before the Big Bang. Awesome. Wow. So we're like, conformal maps are both complex analysis and differential geometry at the same time. And as we all know, differential geometry has a lot to do with general relativity. We want more. So now we're going to read from another book that's been on my shelf for a while. Visual complex analysis. This one is very unorthodox as far as the material from complex analysis that it covers. I remember, so back when I was doing my undergraduate degree in applied mathematics, my favorite class that I did the best, like grade-wise and sheer points-wise on, was complex analysis. That's because the class was only 3, it was graded based upon only the grades you got on 3 exams, 2 midterms, 1 final, and each one was only like 3 to 5 questions, and there weren't any proofs, but they were very, very involved complex variables calculations where you really had to know your stuff and be sharp on your algebraic calculation skills in order to get all the points. And it was taught by this guy, Professor Martin, Paul Martin, who's still there, and he has this British accent, and people would refer to him as the James Bond of mathematics because of his accent. He had this very calm, cool, collected personality. But anyone who got 100% on the exams, he would like point them out when he was handing out the exams in the end. I never got 100%. I only missed like 2 points for like little algebraic mistakes. So not missing things related to knowing the complex variables concepts. It would be something like messing up like a factoring deep within some integral or whatever, right? And so I never got 100%. But I go to this guy's office hours afterwards, right? After the class is over. And I see this book, Visual Complex Analysis, on his bookshelf. And already, in order to have succeeded in that class to that extent, I had already just gone through all the course material the summer before. So I had already learned everything, and then I was just like practicing the old exam problems like all the time so I could get it done like as fast as possible. Anyways, but I didn't get 100% right, but I go to his office hours and I see this book, and I was like, oh yeah, that was like, you know, a weird book or whatever. And he's like, oh yes, that's a very odd book. That's how he described this book. Anyways, it is odd. That's what that rant is all about. But anyways, we're in this chapter here from this book, Visual Complex Analysis by Tristan Needham, chapter 3 on, what do you know? Mobius transformations and inversion. So we have here, in the introduction, the definition and significance of Mobius transformations. A Mobius transformation is a mapping of the form m of z equals, and then a fraction in the numerator we have a times z, then plus b, and then in the denominator we have c times z, then plus d, where a, b, c, d, and z are complex numbers, and a, b, c, and d are complex constants. These mappings have many beautiful properties, and they find very varied application throughout complex analysis. Indeed. So we're going to skip a little bit here, and it says, moreover, these transformations are also intimately connected with Einstein's theory of relativity, which we're about to read about. This connection has been exploited with remarkable success by Sir Roger Penrose, C. Penrose and Rindler, 1984. That book which is being referred to is Spinors and Space-Time, Volume 1, the classic, which I only until recently downloaded, so I don't have much commentary beyond that, but reading on here, the connection with Einstein's theory of relativity. And so we have some stuff about, like, you know, three-dimensional space plus time is a four-dimensional coordinate system because time is just another, it's just analogous to space in Einstein's view, so we lump it all together with 4D. We all know this. And observers that are in motion relative to each other will disagree about the simultaneity of events, but then you can have the equivalence x tilde squared plus y tilde squared plus z tilde squared equals x squared plus y squared plus z squared. And we have Lorentz contractions, Lorentz transformations, all this good stuff. And then we come down here. Now imagine that the space-time coordinate origin emits a flash of light, an origin-centered sphere whose radius increases at the speed of light. It turns out that any given cursive L for a Lorentz transformation is completely determined by its effect on the coordinates of the light rays that make up this flash. Here is the next crucial idea. In example 8, which I'm not going to go over explicitly right now, we explain how we may set up a one-to-one correspondence between these light rays and complex numbers. Very interesting. Thus, each Lorentz transformation of space-time induces a definite mapping of the complex plane. And here comes the punchline that I've been building up to. Thus, each Lorentz transformation of space-time induces a definite mapping of the complex plane. What kinds of complex mappings do we obtain in this way? The miraculous answer turns out to be this. The complex mappings that correspond to the Lorentz transformations are the Mobius transformations. Conversely, every Mobius transformation of the complex plane yields a unique Lorentz transformation of space-time. And then it says here, even among professional physicists, this miracle is not as well known as it should be. So I hope if there are any professional physicists watching out there that you already are aware of this miracle. I'm going to read a little bit more and then I'm going to start skimming the rest of this here. The connection exhibited in this quote about Mobius transformations being the complex mappings corresponding to Lorentz transformations is deep and powerful. Just for starters, it means that any result we establish concerning Mobius transformations will immediately yield a corresponding result in Einstein's theory of relativity. Furthermore, these Mobius transformation proofs turn out to be considerably more elegant than direct space-time proofs. To really understand the above claims, we strongly recommend that you consult Spinors and Space-Time Volume 1, published in 1984 by Sir Roger Penrose and Rindler, after reading this chapter, which I might do, but I'm going to skip further down here. And so this is like an exercise left to the reader thing. You could decompose the whole AZ plus B over CZ plus D Mobius transformation into 4 steps. First step is a translation. So we have this here, step 1, Z mapped to Z plus D over C. Then we have Z mapped to 1 over Z, which is an inversion, which I'll touch on in a sec here. Step 3, we have an expansion and a rotation here by negative AD minus BC over C squared. And then finally, step 4, we have another translation, Z plus A over C. Why is this important? So conformal mappings, like we were just talking about, are transformations, mappings where angles are preserved. And so obviously with translation, expansion, and rotation, we see why angles would be preserved. But then with the second step in breaking down, decomposing the Mobius transformation, we have this 1 over z, which is an inversion. And so really, if we want to show that Mobius transformations are conformal, then you have to show that these complex inversions are conformal. And so when you geometrically break down what inversion of a complex number is, you have the unit sphere, or excuse me, you have the unit circle in the complex plane, and you move points that are inside the unit sphere to the outside, or points that are on the outside to the inside, vice versa, right? By taking the reciprocal of the radius of that complex number, right? And then you also flip the angle of that complex number. So there's two aspects to complex inversion. There's inverting it with respect to the unit sphere, and then inverting or mirroring with respect to the angle against the real numbers. Okay, so turns out that inversion of complex numbers is conformal. Okay, yeah, this chapter in this book is really good, and there's parts about things like stereographic projection, which are coming up in future sections in the differential geometry book. So it's really cool to check out the intersection of differential geometry and complex analysis ideas. I think right here we have one of my favorite topics in math. You could say the Riemann sphere, the point at infinity. You could say that you could map the complex plane to these Riemann spheres where one of the poles is the so-called point at infinity. And this was actually in a section from the Wikipedia page on conjugate diameters, which I was reading that Wikipedia page in the last episode, but I skipped this section, which I'm referring to now. So in the conjugate diameters Wikipedia page, there's this section here in projective geometry. So conjugate diameters in projective geometry, it says, every line in projective geometry contains a point at infinity, also called a figurative point. So this is the same point which is at the pole of the Riemann sphere, which I just mentioned, which you could map one-to-one the complex plane onto these Riemann spheres. But continuing from the conjugate diameters Wikipedia page, the ellipse, parabola, and hyperbola are viewed as conics in projective geometry, and each conic determines a relation of pole and polar between points and lines. Using these concepts, two diameters are conjugate when each is the polar of the figurate point of the other. Anyways, but we are reading about the Riemann sphere here. Just to wrap up talking about this Mobius transformations chapter in the visual complex analysis book, because this is just a cool topic, I think. So when you have these Riemann spheres, which are mappings of the complex plane into 3D in a way, we have right here different kinds of Mobius transformations on these Riemann spheres. So we have the elliptic, hyperbolic, loxodromic, and parabolic Mobius transformations on the Riemann sphere depicted here. And I just think that that is a really cool idea. So now we are finally going to, this may seem like another random point, but when we're talking about classifying points on surfaces as hyperbolic, or you could also call a hyperbolic point a saddle point, or we're talking about just now hyperbolic Mobius transformations on the Riemann sphere, we need to remind ourselves also what just is the definition of the equation of a hyperbola in a plane, like from Algebra 2. Anyways, we need to not forget the basics and the fundamentals, right? Anyways, thank you, Ambrosia with 3 A's, for your great comment. And with that, let's get on to the reading. So we are in Section 61 on page 193 on conformal mapping. The angle between two intersecting curves is, by definition, the angle between the tangents to these curves at the point of intersection, for which refer back to section 35, on measurement of lengths and angles in a surface. An allowable mapping of a portion S of a surface onto a portion S star of a surface is called angle preserving or conformal if the angle of intersection of every arbitrary pair of intersecting arcs on S star is the same as that of the corresponding inverse images on S at the corresponding point. The name conformal was introduced by F.T. Schubert in his 1788 work De Projectione Spheroides Ellipticae Geographica. Conformal mappings are important in cartography, for which refer to the upcoming section 65 on conformal mapping of a sphere into a plane and stereographic and Mercator projection. So look out for that if it's not out already. So the stereographic projection was introduced already by ancient Greeks. A systematic theory of conformal mapping was developed by Euler, Lagrange, and especially Gauss. Necessary and sufficient conditions for a mapping to be conformal are as follows. And this theorem, the proof is going to take up the entirety of the section, and then there's one really hefty problem at the end. So here we go. Theorem 61.1. An allowable mapping of a portion S of a surface onto a portion S star of a surface is conformal if and only if, when on S and S star the same coordinate systems have been introduced, the coefficients g sub alpha beta and g star sub alpha beta of the first fundamental forms of S and S star respectively are proportional, namely g star sub alpha beta equals nu in terms of u1 and u2 times g sub alpha beta, where nu is greater than 0, and alpha and beta respectively can be 1 or 2. The proof is as follows. That this condition is sufficient follows immediately from the relation 35.5, which is that if we have a surface with a vector parametric representation x with coordinates u1 and u2, where on that surface we have intersecting curves c and c star. So the way we're going to represent these curves is that we have, for the curve capital C, for the alpha coordinate dimension, we have that represented by the function h superscript alpha in terms of the parameter t, where alpha can be 1 or 2. So, for example, if we have the second coordinate dimension on the curve capital C, it would be u2 is the coordinate direction, but this is then given by the function h superscript, in this case 2, of the parameter t. So similarly, for the curve capital C star, the coordinate directions u alpha are given by these functions h superscript alpha star of parameter t, where alpha can be 1 or 2. And where gamma is the angle between these vectors v and v star, let's say, where v is tangent to the curve C at some point capital P on this surface capital S, and the vector v star is tangent to the other curve C star, but also at this same point capital P on the surface in consideration here. So we have that the cosine of gamma is equal to a fraction with a numerator which is the scalar product of v with v star, so the scalar product of these two vectors tangent to the curves on this surface at the particular point, over a denominator which is the magnitude of each of these vectors multiplied with each other. So we have the magnitude of v times the magnitude of v star. Well, this cosine of gamma is then equal to a fraction with the numerator which is g sub alpha beta, then times h superscript alpha prime, then times h superscript beta star prime. So then in the denominator we have the square root of the quantity g sub mu nu, then times h superscript mu prime, then times h superscript nu prime, closed quantity, then times the square root of the quantity g sub sigma tau, then times h superscript sigma star prime, then times h superscript tau star prime closed quantity. So this relation for the cosine of gamma is to say that these curves, C and C star, which are on the surface, S, these curves are orthogonal at the point capital P if and only if G sub alpha beta times H superscript alpha prime times H superscript beta star prime is equal to 0. That the statement of theorem 61.1 that G star sub alpha beta equals nu in terms of coordinate directions u1 and u2 then times G sub alpha beta, where this nu is positive, that this condition is sufficient, follows immediately from that cosine of gamma relation, since the proportionality factor nu occurs in the numerator of that relation for the cosine of the angle between two vectors which are tangent to curves on a given surface, as well as in the denominator. We will now prove that the above condition is also necessary. Oh, look who it is. It's this little boy, this grown man. Let a conformal mapping of the portion of a surface S onto the portion of a surface S star be given which, in consequence of the special choice of the coordinates u1 and u2 on S and u1 star and u2 star on S star, takes the form u alpha star equals u alpha, where alpha can be 1 or 2, for which refer back to the preliminaries of mapping section at the beginning of this chapter. Let capital P be an arbitrary point of an arc C1 on the portion of a surface S, and let du2 to du1 be the direction of the tangent to C1 at P. The image point P star of P has the same values of the coordinates as P. The equations by which C1 is represented on S represent also the image C1 star of C1 on S star. The direction of the tangent to C1 star at P star is therefore given by the above value du2 to du1. Consider now on S another arc C2 intersecting C1 at the point P, and let delta u2 to delta u1 be the direction of the tangent to C2 at the point capital P. Then the angle alpha of intersection of those two arcs at the point capital P can be obtained from the relation sine alpha equals the square root of G, then times a fraction with the numerator of the magnitude of du1 delta u2 minus du2 times delta u1, all over a denominator of ds delta s, where ds and delta s are the linear elements of C1 and C2 respectively. As per the relation similar to the one given for cosine gamma just a moment ago, but this time we're looking at a relation in 35.8 for sine gamma, we denote by C2 star the image of C2 on S star. The direction of the tangent to C2 star at P star is given by the above value delta u2 to delta u1. The angle alpha star between C1 star and C2 star at P star can thus be obtained from the relation sine alpha star equals the square root of G star, then times a fraction with the numerator of the magnitude of du1 times delta u2 minus du2 times delta u1, then a denominator of ds star times delta s star, where ds star and delta s star denote the linear elements of C1 star and C2 star respectively. Since the mapping is assumed to be conformal, alpha equals alpha star. Hence, from these previously given relations for sine alpha and sine alpha star, we have that the square root of G over ds delta s is equal to the square root of G star over ds star delta s star. Taking as arc C2 the directed coordinate curve where u2 is equal to a constant through the point capital P, and as C2 star the coordinate curve where u2 star is equal to a constant through the point capital P star, then delta s is equal to the square root of G sub 1 then times du1, and delta s star is equal to the square root of G star sub 1 then times du1 star, which is equal to the square root of G star sub 1 then times du1. So then, consequently, by the equivalence relation between the square root of the discriminant of the first fundamental form g over ds times delta s with its counterpart, except every variable has a star now. So in consequence of this, we have ds star ds is equal to the square root of g star times the square root of g sub 1, 1, all over the square root of g times the square root of g star sub 1, 1, which is then equal to the square root of nu in terms of u1 and u2. Or we have that ds star is equal to the square root of nu in terms of u1 and u2, and then times ds. In this relation, nu depends on the point capital P only, but is independent of the tangent direction under consideration. So since the above relation for ds star ds is supposed to be true for any curve passing through the point capital P, that is, for every value of the direction du2 to du1, we must have that g star sub alpha beta is equal to nu in terms of u1 and u2, then times g sub alpha beta for alpha and beta equal to 1 or 2 respectively at the point capital P. Now, since the mapping is assumed to be conformal at every point of the portion of a surface capital S, these relations hold everywhere on that portion of the surface capital S. From this theorem and theorem 57.1, we immediately obtain the following. And as a reminder, theorem 57.1 is that an allowable mapping of a portion capital S of a surface onto a portion capital S star of a surface is isometric if and only if at corresponding points of S and S star, when referred to the same coordinate systems on S and S star, the coefficients of the first fundamental forms on S and S star are the same, namely g sub alpha beta is equal to g star sub alpha beta for alpha and beta equal to 1 or 2 respectively. So we have from theorem 61.1 and that theorem 57.1, now theorem 61.2. Every isometric mapping is conformal. And finally we get to problem 61.1. Determine all the surfaces of revolution which can be mapped isometrically onto a given surface of revolution of a variable Gaussian curvature. The solution is as follows. For any surface of revolution, the Gaussian curvature is the same at all points of any parallel. Since the Gaussian curvature of the given surface of revolution S is assumed to be not constant, the images of the parallels of the surface of revolution S star to be obtained must be the parallels of S, for which referred to theorem 57.2. Namely, isometric surfaces have the same Gaussian curvature at corresponding points. Corresponding curves on those surfaces have the same geodesic curvature at corresponding points. Since an isometric mapping is conformal, as per theorem 61.2, every isometric mapping is conformal, the meridians of S and S star must also correspond to each other. Let the x3 axis be the axis of revolution of S, and let the vector x in terms of u1 with the three entries. First we have p of u1, then we have 0, and then we have q of u1, be a representation of the meridian capital M of S, which lies in the x1, x3 plane. Let u1 be the arc length of the meridian capital M. Then S can be represented in the form vector x in terms of the directions u1 and u2, which is equal to, entry-wise, pu1 then times cosine u2, and then the second entry, pu1 then times sine of u2, and then in the third entry, qu1. S star may be represented in the form the vector x star with the directions u1 star and u2 star, which has the three entries given by p star of u1 star then times cosine of u2 star, and then a second entry, p star of u1 star then times the sine of u2 star, and then a third final entry of q star of u1 star, where u1 star is the arc length of the meridians of S star. Then we have that ds squared is equal to du1 squared plus p2 squared of du2 then squared, and ds star squared is equal to du1 star squared plus p star 2 of du2 star squared respectively. The meridians on both surfaces correspond to each other, and so do the parallels. Consequently, u1 star depends on u1 only, while u2 star depends on u2 only. Comparing the first fundamental forms and using theorem 57.1, which we already went over, we have that du1 star squared is equal to du1 squared. That is, u1 star is equal to positive or negative u1 plus d. We may set d equal to 0 and take the positive sign, that is to say u1 star is equal to u1. Furthermore, p star 2 of du2 star then squared is equal to p2 of du2 then squared, or pu1 over p star of u1 is equal to positive or negative du2 star over du2. Interesting. The left-hand side of this relation depends on u1 only, while the right-hand side depends on u2 only. We may thus set p star equal to cp and du2 star equal to positive or negative 1 over c then times du2, where c, which is non-zero, is a constant. If we choose the positive sign and set the constant of integration equal to 0, we have from this u2 star is equal to u2 over c. The negative sign would correspond to a reflection, and the constant of integration corresponds to a rotation about the axis. Since u1 star is the arc length of the meridians, we have p star prime squared plus q star prime squared is equal to 1, and therefore q star is equal to the integral of the square root of the quantity 1 minus c squared then times p prime squared closed quantity du1. S star thus has the representation given by the vector x star with the coordinate directions u1 and u2, and is thus equal to the three entries where the first entry is cp times the cosine of u2 over c. In the second entry we have cp times the sine of u2 over c. And in the third entry we have q star, or the integral of the square root of the quantity 1 minus c squared times p prime squared closed quantity du1. If we set c equal to 1, this representation is identical with that of s. A continuous variation of the value of c corresponds to a continuous deformation, that is, a bending. Wow, that is actually pretty intense. Hence, for a given surface of revolution, there exists a one-parameter family of isometric surfaces of revolution. Wow, that last part about the constant of integration c, a continuous variation of the value of c corresponds to a continuous deformation, that is, a bending of this surface of revolution. Very interesting. But that's all we're going to read for today, because this has been a long bunch of ranting and reading Wikipedia. What do you guys think of this outfit combo, by the way? We have houndstooth brown blazer and then blue stripe Oxford shirt, and then we have the red and blue but then with the thin gold stripe tie. This is going with inspiration from an image of this guy by the name of Russell Piter, who was like a guy all about melatonin research. But I'm rocking this with the brown leather gold tank Peugeot watch and the gold pinky signet ring. Also, brown pants, light tan socks. These probably pair well. This outfit probably goes well with the brown tassel loafers then. So let me know what you guys think of this week's episode, this week's outfit, this week's young man, grown man, this black little boy. And I'll see you guys in the next one. Peace.